Exploring linear versus exponential functions. So the first thing that we're going to do is just describe the difference between the two. So linear functions are in the form y equals mx plus b. So that's just your regular slope-intercept form, where we have a constant rate of change. So your slope gives you that constant rate of change versus when we have exponential functions, they have a different equation. It's y equals a times b to the x. And this causes it to, this exponent for the x causes this to have a very fast rate of change. So even if we have like a linear function versus an exponential function, because linear functions have that constant rate of change, so it could be increasing like that or it can be decreasing like that, exponential functions will always at some point exceed the linear functions, meaning that if we have like the same x values, even if the exponential function starts out small, it increases at such a fast rate that its rate will always exceed the linear functions at some point. So here's an example of growth. An example of decay would look something like that. All right. So you could say for both of them, they both have an average rate of change. All right, you can find the average rates of change for both by using that formula y2 minus y1 over x2 minus x1. You just have to remember that for linear functions, you were able to just pick any 2 points. It did not matter which two that you picked, you would get the same slope, the same rate of change, no matter what 2 points you picked. But you just have to remember for exponential functions, it does matter what 2 points you pick. So like if I had points A and B here, that would have a smaller average rate of change versus if I had to take the average rate of change from A through C. So it's still the same concept. You're still plugging in those X and Y values into this slope equation or this average rate of change equation. It's just different for exponential versus linear, because you have to really pay attention to what 2 points you're looking at for the exponential functions. But otherwise, they also have some other commonalities. So like the y in both of these represents the output. So I'll pick a different color. Y is always your output and X is always your input. So if I need to find, for a certain real world situation, what's the output when the input is 3? Well, then I would just plug in 3 for X into both of these and see what I get and compare those two answers. All right. I can't think of anything else right now for comparing and contrasting, but that's just some ideas we'll discuss more in class. All right, but just to kind of put this in perspective for you, this one's an easy problem. This one I'm going to actually skip because it's that easy, something that you should already know. Basically, what does the output represent? What does the input represent? So let's look at this one. We have Marco is studying a type of mold that grows at a fast rate. He created the function f of x equals 345 times 1.3, and that should actually be an exponent. That should be to the x power. So let me kind of fix that for you. All right, sorry about that. To model the number of mold spores per week, what does the 1.30 represent? And how many mold spores are there after 4 weeks? Round your answer to the nearest whole number. So for this, kind of look at it, think to yourself, is this an exponential function or a linear function? Does it look more like y equals mx plus b? Or does it look more like y equals a times b to the x? Well, since this x is an exponent, we know that this is an exponential function over here. And remember when we talked about the growth versus the decay formulas, where we had y equals a parentheses 1 plus r to the t power. Well, since we're looking at what this 1.30 represents, we know that that is this portion of the equation. So we had 1 plus r, and r is your growth rate. So for asking what that 1.30 represents, well, since, and also growth rate is as a decimal. Since that growth rate is the 0.30 plus the 1, then we know that 0.3 represents 30% growth rate. And the fact that it's greater than 1 tells us that it is the growth formula because we're adding 1. If it was decay, it would be 1 minus the growth rate. So the 1.30 represents the 30% growth rate. Now, the other question says, how many mold spores are there after 4 weeks? Round your answer to the nearest whole number. Well, what do I do with that 4? Since 4 represents a time frame, it's safe to say that that's going to be your exponent. You also know that it's your input, so you could think of it 2 different ways, but that's usually the time frame that your exponent represents. So if I just plug in 4 for the x, so we have f of 4 equals 345 times 1.30 to the 4 power. All right, remember the left side is just notation. You don't do anything to the left side, but the right side of the equal sign can be simplified. So I'm going to use my calculator for that. So that was 345 times 1.30 to the 4th power. Should look just like that as it did on your paper. Just entering that into the calculator exactly how it looks here. Oops, sorry. Equals 985.35. So 985.35. And it says round your answer to the nearest whole number. So that means we need to round this decimal to the nearest whole number, which is 985. All right, let's see another example. I don't want to make this video too long, so I'll probably only just do one more. So this one here is a good one. So we have 2 separate bacteria populations grow each month and are represented by these 2 functions. So I'm just going to copy them down here. F of x equals 3 of x and g of x equals 7x plus 6. In what month is the f of x population greater than the g of x population? So notice the difference between the 2. Also, this is actually formatted incorrectly, sorry. Whenever I just copy and paste, it doesn't include the exponent. All right, so sorry about that. So we know that the way that this is formatted, this is going to be my exponential function. And over here, because this looks like y equals mx plus b, this is going to be my linear function. And we need to figure out what month the f of x population will be greater than the g of x. So here's what we'll do. We'll make a table of values, starting with month 1 and just kind of see what we get. And then we'll also make a table of values for the linear equation and see if there is a switch at any point where f of x is greater than g of x. It will happen. We know that it will because exponential functions will always exceed linear functions at some point. We just have to figure out at what point. So what you'll do is you'll plug in the x's into x in the given formula. So I should be pointing at the x, sorry. Same thing over here, we're plugging it in for the x. And I'm going to use my calculator to save time. But I've shown you how to put things in the calculator before, so I'm hoping that's easier now. So 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. 3 to the fourth power is 81. And 3 to the fifth power is 243. All right, now we're plugging in x for this linear function. So 7 times 1 plus 6 is 13. 7 times 2 plus 6 is 20. 7 times 3 plus 6 is 27. 7 times 4 plus 6, so 28 plus 6 is 34. And then 7 times 5 plus 6 is 41. All right, so compare these two tables, and I'll put a star next to which one is greater versus the two tables. So when x is 1, the linear function is greater. When x is 2, still the linear function. When x is 3, they're both equal, but we're looking for when f of x is greater than g of x. So that's not the answer. But then month 4, now it's switched over to the exponential function being greater. So the answer for this one would be month 4 is when the exponential function exceeds the linear function. All right, I hope that was helpful. If you need help with the other problems that we didn't do let me know. I want to kind of keep this video short. But yeah, we're just comparing exponential versus linear functions. This is one of the last lessons. Tomorrow we'll be just reviewing exponent rules. All right, thanks. Have a good one.